The Hubble Space Telescope has had some difficulty with its gyros lately, which are essential to helping it maintain a stable pointing. But how does Hubble actually point? Welcome back to Launchpad. I'm Christian Reddy, your friendly neighborhood astronomer. The Hubble Space Telescope has been in orbit since 1990, and for 28 years it's performed incredibly well. Hubble operates in low Earth orbit, and it's for this reason that the space shuttles were able to access it on 5 different occasions over the last 28 years. And these servicing missions have been critical for Hubble's longevity. But how does a 12-ton telescope actually point itself and maintain that pointing? Well, at first you might think, let's just go ahead and use thrusters. After all, if you fire a jet in one direction, the force exerted by the jet on the spacecraft in return will point the telescope in the opposite direction. That's Newton's third law. But there are, however, 2 problems with thrusters. The first is the obvious one. Thrusters require fuel, and fuel runs out over time. But a second problem with thrusters are that they would create a cloud of gas around the telescope, and that gas could then contaminate the sensitive instruments inside and render the telescope useless. So Hubble needs to make use of a different but very simple method of pointing. It relies on 2 fundamental concepts in physics: the conservation of angular momentum, which is to say the conservation of the momentum of things that rotate, and Newton's third law. For every force, there's an equal and oppositely directed reaction force. So Hubble actually points itself using 2 systems. The first are called reaction wheel assemblies. Reaction wheels make use of these 2 laws by spinning up. They rotate at some speed, and there are 4 reaction wheels on board. By spinning up any combination of any 3 of these at different speeds and different rates, the telescope then rotates in the opposite direction. So for example, if a wheel is rotating clockwise, the telescope will then counter-rotate counterclockwise. And this is done for all 3 of Hubble's axes of roll, pitch, and yaw. The telescope is subject to external torques. For example, the telescope may be trying to rotate in this direction, but pressure from the sun's radiation pushing against the solar panels may be counteracting the angular momentum of the reaction wheel. A second problem is that Hubble can drag against Earth's atmosphere. Now that may seem strange because Hubble is, after all, in space. But remember, Hubble is in low Earth orbit, and that means that it can still encounter fine particles of Earth's atmosphere. Over time, that drag builds up. That means that the reaction wheels, even when they're spinning at their maximum RPM, will not be able to overcome these 2 forces. So Hubble employs another trick to help out the reaction wheels. It makes use of the fact that it's actually embedded inside Earth's magnetic field, and it has these black bars here, these magnetic torque rods, or magnetorquers. These are electromagnets that can be energized off and on as needed to push against or draw the telescope toward Earth's magnetic field. And that gives Hubble a little bit of extra torque to overcome these 2 pressure and drag forces. So that's how Hubble points itself. But how does Hubble know where it's pointing? Well, the first priority of any spacecraft is safety. And in Hubble's case, that means keeping it away from the sunlight. That's why Hubble carries solar sensors on board, which keep an eye out for the sun and warn when the telescope is within 50 degrees of the sun. Now, we don't want sunlight coming right down the barrel of the telescope and ruining the sensitive instruments inside. But we also don't want sunlight to even warm up the interior of Hubble's telescope tube, because that would cause the interior to expand, and that would just ruin the alignment of the mirrors and render the telescope completely useless. So the sun sensors act as a lookout to ensure that Hubble is always no closer than 50 degrees to the sun. But Hubble also makes use of magnetometers, which are mounted around the top of the telescope. These magnetometers are sensitive to Earth's magnetic field and act as a kind of magnetic compass. That lets the computer inside to know how Hubble is oriented with respect to the magnetic field. Now, as Hubble is rotating, it needs to know how fast it's moving and in what direction. And that's where these gyros come in that we've been talking about. These operate on basic gyroscopic principles, and as the gyro is spinning, it becomes very sensitive and very resistant to the motion of the telescope around it. Essentially, the telescope pushes on the gyro and the gyro pushes back as it's spinning. And the amount of the pushback of the spinning gyro tells the computer how fast the telescope is moving. Now, Hubble also employs a set of fixed head star trackers. It's these three items right here on the aft shroud of the telescope. The star trackers measure the position and brightness of stars and feed that information to Hubble's computer, which then matches the patterns of those stars against a star map to help it know where the telescope is pointing. And the final component of Hubble's pointing control system are the three fine guidance sensors. The fine guidance sensors are mounted inside the telescope alongside Hubble's main camera. They look along the periphery of Hubble's field of view to lock on to guide stars. These are pre-selected stars whose positions in space are very well known and are bright enough to easily be tracked. They in turn tell the computer if the guide stars are drifting, and the computer in turn spins up and spins down the reaction wheels as needed up to 30 times a second to correct for Hubble's position. These fine guidance sensors are so precise that they allow Hubble to maintain a pointing accuracy that is the equivalent of holding a laser beam steady on the head of a dime in Washington, D.C., while standing in New York City and holding that laser stable for 24 hours. And Hubble's pointing control system is redundant throughout the entire system. It needs 3 reaction wheels to point, so it has 4 on board. It needs 3 magnetic torquer bars to ensure orientation. It has 4 on board. It needs 2 fixed head star trackers, so it carries 3. It preferably needs 3 gyroscopes to sense its direction and pointing, so it carries 6. It needs 2 fine guidance sensors to lock onto guide stars, so it carries 3. This built-in redundancy is another reason why the Hubble Space Telescope has lasted as long as it has. And best of all, engineers have worked out some tricks to make use of some of these subsystems, such as the extra fine guidance sensor, to make up for one of the missing gyros. So Hubble still has a lot of life left in it, and if you'd like to learn more about the problem with Hubble's gyros, I've made some videos which I'll link to here and in the description below. And if you have any questions about how the Hubble Space Telescope works, or how other space telescopes like Chandra and James Webb work, please let me know in the comments below, and I'll be sure to check them out. And as always, if you'd like to join me on this journey through this amazing universe of ours, well, please make sure to subscribe and ring that notification bell so that you don't miss out on any new videos. Until next time, I'm Christian Reddy, and keep watching the skies.